welcome to the course on FPGA based signal processing systems. We will be continuing with the synthesis of sequential logic circuits. In this first thing, we would be learning this registered logic. What is the meaning of registered logic, in which if a variable is registered or not. Okay, so variables whose values are assigned some values in the synchronization with the clock. Those are called the registered. I mean the variables will be registered at the passage of the clock. If you say that x is equal to some, x is less than or equal to some value, then it is in synchronism with the clock, it is registered. Let's see that these signals will be updated, or these variables will be updated with respect to the clock edge. At every clock edge, either passage or neg edge, which is declared in the sensitivity list, it would be updated. And while if it is registered, if we do that storage with respect to the clock, then it is more stable. It would avoid the glitches also in the variable. We can observe that. So registered variables are with respect to the clock, we have this operation to be done. Supposing, for example, if we take this example, so there is a mux which is having 4 inputs and 1 output. Each input A, B, C, D is of 8 bits. It can be 16 bit or 32 bit, whatever the data size, be A, B, C, D, and output is 8. The select output is also 8 bits. Select is because we have the 4 inputs, so at least it needs 2 bit in the select line, 0 0 0 1 1 0 1 1. So if 0 0, the input AA will be passed to Y. If it is 0 1, then the input B would be given to A output. C, similarly 1 0 or 1 1, the D input will be given to output of the multiplexer. So when we say this is good enough to have the combinational logic in the multiplexer, if we have this mux which is to be registered, the output is registered if we call it, then it should be passed through the flip-flop, and every clock that is at the clock edge, the data input is given to Y. The 8 bit what is selected from the ABCD will be passed on to Q. So how does this make this module? So this is a combinational logic, but to have the output variable which is registered using the flip-flop here, so how do we do that in the Verilog code? So module, this is a mux which is registered here. Output range is 8 bits, that is 0 to 7 Y. Input is clock and select is also 2 bit, and input here ABC, which are 8 bit inputs. Clock and select bit are the 2 here, and this is the input which is ABCD from the previous diagram. It is ABCD, which is 8 bits. Always at the rate passage of the clock, we have case select, that is if it's 0 0, what is the choice? It's 0, then Y is assigned A. If it is 1, Y is assigned B, and else if it is 2, it is going to be the C output, and D will be the output if the choice is 3. It should have the default case, otherwise it would infer a latch. So default Y 8 bit X is assigned to Y, and then end case. So case and end case. So this completes the case structure, as well as this passage of the clock. Instead of level sensitive behavior, we have this variables defined with the passage of the clock. So, okay, so if you don't have this passage of the clock, then it's whether it will be inferring a flip-flop or not. It won't be inferring a flip-flop if you say instead of having this always sub A, B, A or B or C or D, then do this. So there won't be any registered outputs you would be getting. So always at passage of the clock here, it recognizes the clock which is having the edge sensitive behavior and the flip-flop. So here we have the inputs, which is A. The RTL schematic shows that 0 0 this is a mux structure, B 1011 the 8-bit inputs and the output 0 to 7. So, the RTL mux, which is only which has the select bit only having 2 bits, you can see there is no control logic in it. If we use the ternary operator, or if we have this select line which is having the logic, then this would be having the control logic. You can simply put that to select 0 0 or not. So, it just gives the select bit 0 and 1, and the clock which is making this CLK, and each of the bits, that is here 8 bits of 4 choices. Okay, so given here Q, this is y equal to 0 to 7. So, registers, multiple registers have been given to that in the schematic. So, the clock and the D output from D is getting the data from the mux output. So, this flip flop will be registered. This is helping in registering the variables y, the inputs whatever this A, B, C, D is getting, that can be seen in this as a flip flop over here. Otherwise, this combination circuit only will have the synthesizer give only the mux. This is possible only we have the always at the passage of the clock. So, the technology schematic which is giving this A, B, C, D over here, right, and the select bit 2 input, and the clock which is deciding the 1, 2, 3, 4, here 4 plus 8, and 8 of them the registers 0 to 7. So, 8 bits for input and the outputs also have been shown over here. This is the technology schematic which conveys that there is a register, there is a flip flop at the output. So, the registered the corresponding lookup tables or the truth tables on the cell gives the details of all the 8 output bit outputs, that is 0, 1, how these are made. You know what is the, why is it becoming so big? This truth table is 5, and then you can see this even 6, 7, and there are 0 to 7. So, that means 8 bits have been decided like this. It is having some of the, you can see in the code, it has a 8-bit X as well, so default. So, it needs to consider this X for minimization of the logic. So, the cells have this truth table considering all X values also unknown. If it is unknown, the default case, that is considered in the minimization process. So, after this, the registered variable can be obtained with the flip flop at the output. So, for a combinational logic, that is registered in the sense that what we said, we have the output at the, for example, at the output at the flip flop. For example, the data input, we have the shift registers, the shift register with 4-bit. In this data input, a clock which is given for each flip flop. Okay, this is in synchronism. So, it's a synchronous sequential circuit in which the Q output is given to next flip flop. This is over here, and this is over here, and here. So, data input C, A, B, C, and D, and reset for all the cases. And if we take the signal A and invert it, and signal B, the output of the second flip flop, and them, just leave it here with the, want to make some new signal from this and want to be registered with respect to this clock. That means we want to use this signal A and signal B in some other circuit, or you want to see this output and as a the shift register output signal A and signal B, and get a new signal. That new signal is to be stable, okay, so, or to be registered. So, in that case, the same reset and the clock of the register, shift register, is used here also to make the flip flop. So, how do we make this circuit? That is, in apart from the shift registers in the module, we have to have this combination logic which is registered at the output. So module, say registers, this is data input, clock reset, output new signal, and this is new signal D here over here. These are the two outputs. Okay, and even the register signal A, signal B, and signal C are the registers which are fed to the next flip flops, and this signal A and signal B also used in the combinational logic, and all of them are used inside the always block. Always at the rate passage of the reset or passage of the clock. Begin if reset is 1 bit, you can see that what is that, all the registers should be cleared. So that means signal A is 0, signal B is 0, all flip flops should be cleared, C is 0 and D is 0, and new signal is also 0. So as we are declaring here this new signal 0, so it is inferring this as a flip flop. Then another flip flop with respect to this clock edge begin if reset is this, and else, so it decides that the reset, this is not a clock, because else what is the condition over here, else begin again the number of statements. Data input is assigning to the signal A. It's a non-blocking assignment, which you can see the difference in this sequential logic. Non-blocking assignment where signal A is assigned to signal B, and C and D are getting in the similar way. Also the new signal, which is signal B and not of signal A and them, and which is given to the new signal of the register or the flip flop over here, which is main. This is the case which we have end. So this is giving the else condition. So all of them are synchronism with the clock edge, passage of the clock. So this formation, we have seen that if we have the non-blocking statement, it would inform different D flip flops, 4 D flip flops. If it is blocking, that will be parallel flip flops. We had also already discussed this in the previous lectures. Like, so the non-inverting or the case of having here only one clock. In the previous example, we had the ripple counter, which has the clock from one to one output of one flip flop to the another, whereas here this is having the only the passage of the clock and do this operation. So this is a shift register, and this shift register certain outputs are taken to use it in the next block, and which needs to be registered. So this is a new signal which is formed from these one, and because of this new signal, so we have, it is creating a flip flop over here. This is again the D flip flop. You can see this is the output which is called registered output. The signal is registered now. And that means it will avoid the glitches, it will work in synchronism with the clocks of the shift register. So the RTL schematic for this signal A, B, C and D, the clock and then clock and clock over here. Same clock is given to all the flip flops, and data input from Q, the another data input, your data input. Also you can see the new signal which is having the same clear signal, and the clock from there. The invert and AND operation is a combinational circuit which is forming the new signal, and that is registered over here. It's a new signal. This is the output of the registered signal, that is new signal. It's the same technology schematic which shows them as the C is not used, and the 1 flip flop, 2, 3 and 4 flip flops of that. The new signal which is having the logic, combinational logic, invert and with the other one. So I1 is here, and this is taken to I0. I0 and I1 are signal A and signal B is here, and the output of this is here. This is the flip flop which registers this output new signal. So you can see the technology view. So the lookup table here, the truth table can be, see when taken it invert one signal is invert and then AND. So this function is realized in the truth table. The combination logic is realized in this truth table. So you can see this technology schematic which shows this extra flip-flop over here, because the new signal is again at the influence of the passage of the clock. Okay, so passage of the clock, if you have these variables, are taken as the registers 2, 4, 3, 4. So unregistered, so how do we make that the same thing which is doesn't have any flip-flop at the output? So the same shift register which has them and taken signal A and signal B, but it should not be registered. So it should be taken out of the passage of the clock, synchronizing signal influence. So how do we do that in the module? Register, input data in, clock reset, output new signal and register. Here register signal A, signal B and signal C. Still this is output and reg. You can see the same declaration over here, but always at the rate passage of reset as passage of the clock. So next, if reset is 1, declare all of them as zeros, that is assign this A, B, C, D zeros, and there is no change over here. And you can see that new signal is not given or not initialized, okay, if there is a reset. So it is not under the influence of this passage or reset or passage of the always block. It is not coming into picture. And if reset is 1, that is the case. If else reset is 0, data in, assign it to data signal A to B, and then B to C, C to D, and you can see here we have taken out of the new signal from its always passage of the clock, the influence of the passage of the clock, and declare them as a separate combinational logic continuous assign statement. Assign new signal equal to tilde signal A and signal B. So this is assign statement which is not inside the always block. Okay, so now the new signal is taken out of the influence of this passage of the clock. Now the realization of this, let's see that signal A, yes, it is at the passage of the clock, B, C and D, and the B is taken and A is inverted, yes, and a new signal is formed because we have the assign statement separately and we did not even initialize that inside the, if reset is 1. So it is not under the influence of passage of the clock, and this new signal is only a combinational logic. Over here you can see the absence of the flip-flop. This signal is unregistered now. So because of this unregistered signal, that is, it won't be stable like the previous case with respect to the clock, but now here this is only a combinational logic. And so if you declare a variable inside the passage of the clock, it would infer this flip-flops here, otherwise it would be unregistered. The combination logic can be a separate, but it is a continuous assignment now. It is not with respect at the passage of the clock. It is a continuous assignment. What is available over here will be taken here at the new signal. Technology schematic, yeah, the same thing is first flip-flop. Here again the flip-flops, the for A, B, C and D, and the clock which is going over here everywhere in all the cases, and the clear also can be observed. The D input and the D input from one on the another, this is another one and D, but the combinational logic which is similar to the previous case, it takes the output from here and here to the lookup table, and a new signal is formed. This new signal, it doesn't have the flip-flop at the output, which is not under the influence of the clock. So this is a technology schematic. This is unregistered case. So the output, which is as the case of the truth table gives this, the LUT truth table is one invert and the AND of the two signals here. So every sequential model now from this in your design should have a reset signal. So the global reset, otherwise this initial state of the machine cannot be controlled. So if you put it the reset, so if it keeps shifting and we want to make all the shift register all the flip-flop outputs should be 0 0 0 or clear it. In that case, we can have you should have reset signal. Otherwise, you will not be having 0 0 0. You cannot bring it to the initial condition if the state shift registers keep on shifting, or any state of the machine cannot be controlled. It is so advisable to have this reset signal in the design. The first statement of the behavior that is associated with the reset signal must be conditional statement, and that terminates the execution of the behavior if the reset signal is asserted. So it's obvious that always at the passage of the clock, if reset do that operation, the first statement should be if statement, that conditional statement which can help to reset or control the states using them, the reset signal. If it is asserted, all of them will be clear. So the state movement of one state to another, the shift registers or the counters, all of them should, the state machines also, we have this, the reset signal should be used in the design, and it should be the first statement after always at the passage of the clock or the state memory creation. So coming to this gated clock or the clock enable, in this, suppose we have seen in the flip-flops that clock enable CE is put as 0 in all the realization RTL schematic under the technology viewer. We have seen the C is given 0. So how do we, in one case the toggle is connected to that CE. Okay. So now if we see that gated clock, for example, in this module gated clock, we have this input clock reset data gate. This is the gate data. There is a difference. So output is given reg and q. So for example, always at passage of the clock or negage of reset, this is fine. So there are two signals over here. If reset is 0, q is 0. If else if data gate, if data gate is true, data equal to q. So either you use reset as 1 or 0, that is fine. If it is 1, then make it 0, else if data is 1, this one. So here we have used the negage of the reset. So it is reset is 0, then q is 0. So the case is data is stored to q. This is inferring the storage, else if statement, data gate. Okay. So we have seen this, there is a data gate and the data. Okay. So data is also the input here, and data gate is also an input. So let's see how this is going to be inferred in this. In what is the case in which we need to use the gated clocks. So the clear, which is negate and the passage of the clock, data gate is given to C. You can see that D. So for example, if you have the clock or a 50 megahertz clock, you want an operation to use this clock of 50 megahertz. These are the passage of the clock wherein you'll be using the data to be assigned or something. So that if you want to restrict this clock period, so I want to use it for suppose up to this 1 2 3 4 5 6 7 clock edges. I want to make this clock to be used in the data, and after that it should be 0. The data need not be operated, or this it need not be assigned to a queue. So the clock, using this clock, we form a gated clock that can rest for, I mean, that is available for a certain period of time. That means this clock is gated to up to 1. There are logic to develop this gated clock as well. So this is the data gate, which sometimes here uses q and also q and clock to make the data clock. That's also possible to have actually in the logic. So this is the gated clock, gated one, the data, and in this case, yes, the passage of the when it is 1, pass this D, whatever is the D, and Q can be passed to D and Q. Data available here can be passed to every passage of the clock, or when it is 1. it is 0, then don't consider this clock at all. So don't use this. So this is the meaning of the gated clock or gated data. So the data is used in this period and not in the other period. So this can be developed. So this is the one which is given here, data gate, that is C, the clock which is constrained for some period of time and then not assigning this data to Q. So the technology schematic in which that you have this clear, which is if it is 0, 1 and or 1, it is 0, is one input LUT, and you can see the data and data gate which is having the C, okay, in the flip flop. So clock is anyway fine, but if data gate, then give it to C. So one example is if reset in the if statements, that uses that it is not the clock, and then if data gate, in this case another else if statement, if data gate and do this operation, assign this to this, or so if there is no else statement, then this, that is assigned to CE, okay, and the data is given a D, given it to D here. So this is the one input LUT, 0 into 1, it will be 1 for 1, it is 0. So now the gated clock, what we had seen module, gated clock input clock enable data output register Q out. Always at passage of the clock, if enable, store the data to Q out. Again, this is the passage of the clock, and you can see the if enable, there is no reset in this case, though the clock is enabled for some time, and then the data is passed. This is also the another way of doing this, enable clock enable, using the clock enable. So schematic, you can see this enable is connected to CE, clock and D. Then technology schematic, similarly the CE takes this enable, okay. So how much time I can restrict the clock use for assigning the data to Q, that's the thing of C. So if in the always block, apart from reset, if you have else if condition, that goes into the toggle. G flip flop also toggle is connected to C, if you see, as we have noted in the previous examples. So now this is for the gated clock and the how to use this clock enable as well. Okay, so you can have this clock enable can be reduced clock. You can say, suppose it is 50 megahertz, you can reduce it to for 10 cycles of only, and rest of them 0. Again, you can have it for the another 10 cycles on, and so on. So if you consider the data types, how these are getting synthesized. So the module data types, example, this module is data types. If you have this input ABC, for example, output is sum1 and sum2. Assign statement with sum 1 A B C all of them. Assign another assign statement which has sum2 A plus B within the bracket plus C plus D here. So how this is getting realized, this data types. So it takes A B C, first take A and then add B. After that AB is added, then C is added, and then after A B C D is added. So it's moving from the left to right. If you don't have any parenthesis shown or the bracket, the synthesizer would try to synthesize these adders. So like from left to right. If you clearly specify the brackets or the precedences, then first A and B are added, and then C and D are added. This sum and this sum are added next. So it is adding the A and B over here, and C and D over here, and then another added which is getting the sum2. Okay, but in this case you have, suppose a bit exceeds here, for carry you may have, suppose it is 4 bits, it will be 5 bit, and 4 bit again it will be 5 bit. Okay, so this would have some, if it exceeds another 5 bits, so other will be 4 bits. But in this case you have 4, and here adding it, this would have one 5 bit, and another if you have A, and then here is B, and then C is added over here, and then D is added to this. Okay, that's a sum 1. Okay, here every stage need to have this this is having 5 bit, 5 bit, and then 5 bit for adding if there is a carry here. So you can see the addition make, this is also having the three of them, but you have the steps increasing addition in this process, and this is faster, this parallel addition is faster than this mechanism. So it is the preferable way to have this data types is the second one. So let's see the RTL schematic here, how this is synthesized. AB is added, in both cases it is required, okay, A plus B, and the first stage. Okay, so after this is given to here, this is for sum 2, this is the one, and C and D, this is added in this 1, this 2 and 3, these 3 are in the first case, then second sum 2, and this 3 A, B, C, D, and C is added here, and then here we have the D which is added over and get the sum 1. So if there is any carry, then every addition should have the 5, suppose it is 4 bit and you have the 5th bit also, okay. So for every addition, so that bit addition is depends on the A, B and C, D inputs, but the way in which the addition is done is the first, second should be faster than the first one mechanism. So the data types can be given clear brackets so that you can have the faster operations in the schematic. So technology schematic, which is not showing all the details. Here I0, I1, I2 and I3, there are 4 input LUTs are used, which gives sum 1 and sum 2. The output is made here as you can see 4 inputs are taken and all combinations have been tried over. In the output you can see the truth table, which is taking all the 4 inputs and then try to minimize it. If you have it in the same code, sum 1 and sum 2, you have it in different one, you can see the different is mentioning that this function will be different for first sum 1 and next sum 2. So in the case of sequential logic synthesis, wherein we have decided the registered one and unregistered one. If you want the registered, you need to put that variable under the influence of passage of the clock. If it is out of the influence, then it will be registered. It is better to have the registered variable to avoid the glitches, and it will be more stable. So what is the meaning of registered and unregistered variable? How it is in the flip-flops are synthesized. In that case we had seen with a combinational logic and the sequential circuit, which has a combination logic and registered output. The data types, how to handle this data types also we had looked into. We have this case of different, the faster operations is better to have it, and gated clock is some of the cases the clock is not necessary to have the operations for throughout the module. For some portion of this clock it can be used for the operation of the module. So then gated clock is preferable, or enabled clock is preferable for a particular duration of time, and then it is not used. Suppose for some 8 cycles of clock or few cycles of clock can be used, and the module can be made in such a way that the clock can be reduced for a particular period of time on, and the next period off. So with this we complete the synthesis of combinational and sequential logic. We'll do the synthesis of the state machines. A few examples we did in the previous lectures, like sequence detector and the style 1 FSM, in the coming lecture. Thank you.